We have a really great treat. Dr. Stephen Alexander, a PhD from LSU, and Christian Boyer, and there's the two of you guys, are here today to talk about some future technologies based on their experience and research in both 3D printing and vascular anatomy and work with inflammation and how that interacts with vessels. And so Dr. Alexander will be up first. Looking forward to a really great talk.
Thank you very much. I'd like to thank the organizers for letting us present some of this work to you. So I'm going to talk to you today about novel tissue engineering materials and approaches that we're using in my laboratory for creating some 3D stent and vascular prostheses. And so as disclosures, I'm in the Department of Physiology, Chris is in the Department of Oral Maxillofacial Surgery and Medicine, and Spencer Hurst is a participant in the SMART program, generated a lot of these data really recently. I think we all here would know that there are several problems with stents, access grafts, and valves. In the design of them, we're trying to overcome some of these problems. And it's obvious that some of the problems have to do with the fact that these devices must be immediately compatible with foreign blood elements and with the body when they are implanted, which actually limits us to PTFE and several other classes of materials which are non-endothelialized in most cases. And these devices require the lifelong use of anticoagulants in many cases, and that complicates therapy as well. This also anticipates the ingression of media from the body. The body tends to grow in an inappropriate manner around these implanted materials. This is a significant cause of graft failure and device failure. We're trying to overcome that. And if we could do something to improve the integrity of the devices with endothelial and stem cells and smooth muscle cells, then we'd be able to improve the survival of the replicants and integrate them better within the host. So when we're looking at synthetic heart valve failure, tears, perforations, valvular thrombosis, these are some of the things that I've been talking about. The stiffening of the valve leaflets, all of these things may actually be due to the fact that we are inappropriately seeding these with the right cell types. It's also a cause of bacterial infection. Vascular stent failure, again, there's restenosis, there's detachment from the artery wall. Infection is a significant problem in this case. Vascular access graft failure, we have frequent graft thrombosis, and again, bacterial infections. And you have hyperplasia, usually beginning at the venous side that progresses towards the arterial side. So if we could do something to make these materials better, well, that would be excellent. But as I said, it's a double-edged sword. Materials have to be immediately compatible upon implantation. So in an ideal world, if we were able to use PTFE and materials in a way that would be optimized, would be much better. However, we know that that doesn't work. It does require drug management, basically to manage thromboemboli. Cheese grating effects of stents trigger thromboemboli. That's a significant problem that we need to continually address. Even when you were to take for a cabbage of a bypass graft, even if you were to take a vein and implant it to do the job of an artery, we don't frequently arterialize appropriately, and there are weak substitute arteries. Even in the case where you can get an artery out of a patient, frequently those arteries come from an individual who may already have cardiovascular disease, and those vessels don't work extremely well. They have some degree of ongoing medial hyperplasia already. So the endothelial cell is extremely important, and endothelial cells prevent a lot of the problems, so we need to add them somehow to them. Similarly, muscular investment is extremely important. We want to overcome that. So in my lab, we started out trying to take the materials that are currently used, like silicone, like Teflon, and trying to improve them. So our first steps were to take polyethylene, polysulfone, and gelatin, and polydilactate, and coat those onto materials to make them more biocompatible. And this shows that we can create many different layers here. This is showing that we can create multi-layer coatings that will actually support cell cell lining that we see here, we're actually able to coat them in a way that we can put endothelial cells on them, and that might be one approach to going after it. But these coatings are not durable for the long run, and so we had to come up with something a little bit more effective. We can, however, I'll show you this, we can actually create restricted layers where endothelial cells can be selectively seeded, so we can create different types of seeding processes, almost like a jet printer using appropriate coating materials. Now, endothelial cells are not just putting an endothelial coating on there is not necessarily enough. In most cases, you want the endothelium to be functionally normal. And in this case, what you're seeing here on the left are endothelial cells cultured in the absence of flow, and on the right, this is very important, endothelial cells cultured in the presence of physiologic shear. What do you notice? These cells are actually aligning with physiologic shear, and they begin to do interesting and important things in terms of what we're after. We want the beneficial things that endothelial cells do when they're exposed to shear, and those could include the expression of a lot of important and trophic genes, and the suppression of other pro-inflammatory genes. So shear is known through several different processes I won't get into right away to induce nitric oxide, and this is through the benefit of several transcription factors, KLF2, KLF4, and APP, which triggers an appropriate endothelial response, which limits what actually happens to the engrafted material. So in terms of vascular barrier disturbances, abnormal endothelial signaling that would be observed in the absence of flow, endothelial shape and gene expression changes, as well as the effect of those mediators on vascular smooth muscle gene expression, vessel remodeling. All of those things can be controlled better if we have an endothelial layer that has been exposed to shear. So if we have the most important consideration for us is the immediate binding of plasma proteins, especially coagulation factors, and the binding of foreign blood elements to the graft is extremely important. And the good control of that actually will lead to limitation to the binding of these cells, migration across the endothelial layer and into the pseudo-intimal, pseudo-subintimal space. The binding of platelets in these, we need to control that. That can be either controlled by drugs or controlled by having an appropriate endothelial layer attached to it. That's what we're working towards now. These are some pictures here. These are bovine arterial endothelial cells that are coated on some beads. These are lung microvascular endothelial cells. These are bovine retinal endothelial cells. We have a large variety of different cells. That's my lab's expertise. We culture cells from a large number of different sources, and now we're working towards using stem cells to differentiate these cells inside of the graft into endothelial cells and other desirable cell types that we need to create these synthetic vessels. So exposing endothelial cells to laminar flow and appropriate shear stress is not as easy as one might imagine. This is an approach that we've taken in my lab to expose cells to physiological shear. Just show you. And can you run this animation? Can you click on that animation on the screen? Okay. Okay. Yeah, that's good. There is going. Okay, so what we're doing in that is we're actually putting these cells on a platform that's actually inducing physiological shear to them, and that actually triggers a lot of the genes. This is the average. I can show you. This is the average wall shear stress, which approaches the physiological shear, and then we can see exactly what happens on some of these synthetic grafts. So if you were to look at static cells versus cells exposed to low physiological shear versus cells exposed to higher physiological shear, we do several of these experiments. We can collect large numbers of these cells cultured on some of these synthetic matrices that we're working on. I'm going to dance fairly fast through this. The idea is that we're able to promote well-attached monolayers, expose them to different levels of shear to see exactly how we want to induce these. And expression of eNOS, endothelial nitric oxide synthase, goes up very, very abundantly. And that's really what we need. The cells are, now this isn't just the nitric oxide production, this is the production of the protein that yields nitric oxide. So this is like having a nitric oxide donor in place. Now, one of the things our lab is going after are the microparticles. This is a circulating subset of particles that are derived from those endothelial cells, and this may tell us how we're doing in graft survival. And this is something that we measured through a liquid biopsy of the individual who's received it. So to digress now into materials that we're going to be using, or what Chris is going to talk about. Right now, polylactic acid is an important material that's being used in the absorb stent. I know a lot of people have not been extremely satisfied so far with the PLA materials. Polycaprololactone is another biocompatible material that we've looked at extensively in the lab. We're very excited about polyvinyl alcohol, and Chris will tell you about some of our polyvinyl alcohol materials. And polyvinyl alcohol can be polymerized after it is 3D printed. These are two 3D prints, and you recognize this is a vascular stent model. And after it's appropriately hydrated and then cross-linked, we have a variety of different very gentle cross-linked materials. We can create completely water-stable, protein-binding stents and a variety of all sorts of different materials. We're going to put these really on hard valves. And I'll show you. Now, when we have those, it's important that we infuse those with growth factors. If we were to take these stents and put vascular endothelial growth factor into them, well, then we can invest them with a blood supply that actually matches what the body has. It makes it much more biocompatible. Now that's good. It promotes vascularization, but it also triggers immune cell infiltration. So this has to be done in vitro before the graft is actually planted, as an example. So what you see here, you see this? These are endothelial cells that are actually undergoing vasculogenesis, and we put them on these matrices. They will spontaneously form tubes in the presence of these growth factors. Just to show you again, what we're really talking about is if cells are exposed to either tumor necrosis factor or VEGF, they behave the same in terms of neutrophil binding and in terms of T cell. So we want to do this in vitro and accomplish the angiogenesis before it's actually implanted, so that we actually avoid the immune cell infiltration. But we are actually able to do that. We're actually able to promote in vitro vascularization prior to implantation of these materials. So I'm going to set up Chris's talk. This is some 3D printed XL cross-linked polyvinyl alcohol. Some of the things that we see with current biologics and mechanical valves. We now are looking at these things in terms of replicant valves, and these replicant valves, I'll show you another video here. These are endothelial cells growing very nicely on top of these polyvinyl alcohol matrices. They can be modified so that they can be electron dense and can be detected on X-ray. And a lot of these stents have now been incorporated. We used a model where we used collagen gel traction assay to incorporate cells into these collagen gels that are then put on top of some of these synthetic matrices. So we're trying to duplicate in the lab some of the materials and approaches that are used in spheres. And this is constructed from pericardial patch material. So this material, this is going to be echoed in Chris's talk. This is the Edward Sapien transcatheter heart valve that's made of a variety of different materials. We're taking it, putting it all together. What you'll see in a few minutes is that 3D printing creates a limitless and patient-specific number of devices. They're cell and tissue compatible. It incorporates endothelial and vascular smooth muscle. It's functional and durable. And I'm just going to let Chris take over at this point and tell you about exactly how we're accomplishing this using 3D printing.
Thank you, Steve. It's an honor to be here today. And just to start by a show of hands, how many currently own a 3D printer either at their practice Okay, so we have one. I think in the future you're going to see these numbers increase as we progress and with the advancements of the technologies and the prices go down. So just to begin, the objective of this research is to create an inexpensive, on-demand, storable bioscaffolds with the use of 3D print technologies, and this requires a lot of different disciplines, material science, chemistry, engineering, and much of the 3D printing has become real popular in science fiction and both literature and popular media. And by after this talk, I hope you'll have much more interest in 3D printing and potentially maybe use some in some of your research or practice. So just a quick introduction to 3D printing. It's an additive manufacturing technique. It generally uses CAD/CAM technology, which is computer-aided design. You can create a variety of different products by layer, and it allows for really complex geometries and intricate patterns, which is really useful for replicating parts of the body. And there are many types of 3D printing currently, and the one we're going to focus on today is FDM. It's a fused deposition modeling. And the way it works is it uses a filament or a gel, and you create a structure layer by layer. But just to point out another one, the clip technology is continuous liquid interface production, and it uses a resin base with a UV curable source, and I think that's really the future right now, as it's 100 times faster than most of the other types of 3D printers right now. So be on the lookout for clip printing in the future with a lot of medical technologies. So in FDM printing, some of the parameter considerations to look at is obviously it's a layer by layer fabrication, but infill density and infill pattern are some of the things to consider when designing some of these structures, because you can alter the mechanical properties, the degradation rates, the cell infiltration rates, things like that. And another thing to consider is the printing axis that you print on. So the way you print the structure can also determine mechanical properties and whatever you're trying to discover. So in medical 3D printing, there's a typical workflow. Generally, you start off with a medical scan, MRI, CAT scan, things like that. And you can also use handheld scanners to get outer parts of the body. And generally, what you create is a CAD model, which is converted to an STL triangulation. And you run it through a slicing software, which creates a toolpath for the 3D printer. And you run it through your 3D printer, you get a 3D model. And a lot of the current 3D printing medical technologies are based and used to create models for preparing for surgery or to prepare devices for specific anatomical design. And these are just a couple images, just kind of showing you briefly. And this is actually a scan that we did with a handheld scanner, and just showing you we can replicate outside parts as well. And this is just another quick little workflow showing you that this is a CT scan of a patient with a pretty big underbite, and just showing you we can isolate certain regions with software, create a tool path, and then print the model. So this is great, but we're now trying to take it to another step. We're actually creating these models to be used for tissue engineering and regeneration. So I'm not going to go too much into this, as most of you guys are medical doctors and in the vascular realm. So obviously heart disease is one of the leading causes of death each year. More than 5 million Americans diagnosed each year. And the heart valve disease can occur in a single valve or in a combination of 4 valves. And aortic and mitral valves are the most common, usually from stenosis or regurgitation, and there are around 80,000 replacement procedures every year in the U.S. So obviously this is a huge problem. The technologies are great right now, but as you know, in science we're always trying to improve things. And as we're going to show you here in a sec, you'll see some of the technologies we're working on. And some of the ideal characteristics when designing these products is obviously you want it to be non-toxic, you want it to be non-thermogenic, non-immunogenic, tunable materials, like as Steve mentioned earlier, the cross-linking, which adds biofunctionality, such as a charge in hydroxyl and amino groups. And you want mechanical longevity, which, as you'll see in the next slide, this is some of the bioprinting that uses a gel through fused deposition modeling. You can create really good designs with bioprinting, but as far as mechanical longevity, you can just see it's really flimsy gels. And this is actually from some heart valves printed at Denver University. But we're trying to take it to another level as far as mechanical properties and biocompatibility with cell infiltration. And as Steve mentioned earlier, the cross-link PVA, we really think it's a good material to work with. It's really easy to print. You can create all kind of different designs, and you can be cross-linked to add a lot of functionality. And just to show you the cross-link PVA, this is a SEM of a before print. You can see the fused layers. It's pretty rough, but after our cross-linking process, you can see how smooth the fusion is between the layers, and the mechanical properties dramatically increase after our cross-link process. And it also becomes a very stable hydrogel. So Steve has been working on this for quite a while, and myself, and these are some of the constructs that he's designed and I've been worked on too. These are cross-link PVA that has been casted in collagen with smooth muscle cells and then cultured with endothelial cells for growth. And what we've shown is it becomes very flexible and porous and very biocompatible. As you can see in this next, here we go. Okay, so we're trying to apply the same technology to heart valves, and what you're seeing right here is a computer-aided design heart valve that we're working on in the triangulation model. And also, so here's just a quick video. You can see that in the middle, this is a tool path of the heart valve, and this is the actual 3D printing process, and just showing you the CAD model design. So this is a tri-leaflet valve we're working with, and then here's a bi-leaflet. Same concept. We're showing you the tool path, and then so this is a typical workflow you go through in designing and working with CAD models. And as you can see, these materials are very sturdy after printing. This is a polyvinyl alcohol polyurethane blend we're also working on. It's a newer material. As you can see, after hydration, the material becomes very lifelike, and we have surgeons at LSU touch this and they're like, wow, it feels like it just came out of the body. This is amazing. So taking the same technology, we're applying it with the cross-linking process and infiltrating with different cell types and collagen and aortic smooth muscle cells and endothelial cell layers are some of the cells that we're mainly focusing on with these materials, and using these different blends of PVA, polyurethane, PCL. And just to show you, this is the matrix I showed you just a second ago, and these are some of the histological staining and cross sections we're doing with these materials. And as you can see, what you're seeing in the blue is the DAPI, and then the rhodamine fullerene staining the actin filaments and the smooth muscle layers. So this demonstrates the biocompatibility of these materials and how good they are to infiltrate with cells. And here's just another image showing the endothelial layer on the outer portion of the structure, and just also demonstrating the compatibility of these materials. So this is basically the kind of the workflow for the process. We have our cell, we isolate the cells, we can rotate them in a collagen cell mixture, and we culture them, or we can do the casting process. Here's a picture of the valve and culture, and then here's just another example showing the biocompatibility. This is the MTT assay stain, and with the purple, this is before and after, and the purple is basically showing the metabolic activity and the cell infiltration. So these materials are highly biocompatible. And here's just another this H&E stain that we did with these materials, showing the endothelial cellulose layer. And now we're trying to take it to a next step with a Pulsatile flow bioreactor. So this is a device we created. We actually created a timer, and then we have the perfusion with Pulsatile flow, and we have an endoscope that we can kind of monitor some of these structures with. And as you see on the next video, here's an earlier model with the valve under Pulsatile flow. And it's an early prototype, but it just shows you the potential of 3D printing and some of these technologies. And now we're starting to work with self-expanding structures in the same concept. So potentially this could have potential in transcatheter applications, applying these self-expanding structures with the valves in the center, and then cross-linking and adding the functionality. But yeah, in summary and conclusion, so 3D printing constructs can be fabricated in real time using biocompatible materials, permanent, absorbable, or in combination. Bioscaffolds can be 3D printed for vascular applications, we think and hope that, and then expandable structures may be used for transcatheter applications. And then our gas phase polymerization achieves different chemical properties, including stabilization against dissolution and all the other properties we talked about just a second ago. And in the endothelial layer may enhance integration reduce thrombosis or associated drugs with current devices. And overall, the advancements in tissue engineering and 3D printing technologies will help in the development of tissue and organ replacement. And if achieved, more lives could be saved and prolonged. And it is our hope that 3D printing could be the next step in enhancing tissue repair by decreasing costs, adding efficacy, and delivering patient-specific pharmacologic bioactive agents and designs specifically for patients. So yeah, and just to acknowledge a couple of people, this is David Mills. He has a Partners Across Campus grant with Dr. Alexander. They've been a great collaborator, and Jeff Wiseman's been very important in a lot of this research, and Winnie Young is a PhD student that has helped us a lot with a lot of the cell culture. And, yes, thank you.